Okay, let's just face a hard truth right out of the gate. That simple, magical AI demo you just built on your laptop, it's a far cry from the complex, high-stakes pipeline required for a real production system. Welcome to this explainer, where we're going to pull back the curtain and look at what it actually takes to run large language models at a massive scale. We kind of think of AI as this magic single box, right? You ask a question and the LLM simply gives you an answer. That's the prototype. But the reality of production is entirely different. When thousands or even millions of users are demanding instant answers, perfect security, and absolute reliability all at the same time, a single model call just shatters under the pressure. Real production is not a box. It's a highly coordinated pipeline of specialized microservices, all working together in a matter of milliseconds. So here is our roadmap. To understand how enterprise AI works behind the scenes, we're going to follow a prompt through 6 critical layers. 1. Demos versus reality. 2. Routing and planning. 3. Parallel execution. 4. RAG and tools. 5. LLMs and caching. And finally, 6. Full orchestration. Section 1. Demos versus real production. The moment you scale up, you instantly hit a wall of massive bottlenecks. Huge traffic crashes servers, so we have to introduce load balancing. LLM inference costs soar through the roof. We're talking sometimes thousands of dollars a day, so we introduce caching. Hallucinations destroy user trust, so we bring in retrieval and tools. You see, every single roadblock you face when scaling AI maps directly to a specific, battle-tested architectural solution that literally saves the day. Section 2. Routing and Plato. All right, let's actually trigger our prompt. Imagine a user types this specific query into their app. It enters the API gateway, passes securely through our load balancers, and hits the router. The router is the first intelligent checkpoint. It analyzes the text instantly and decides, okay, this isn't a general web search, and it's not a request to write Python code. This needs to go down the finance workflow. By routing queries to specialized agents right away, we save a ton of time and compute power. Once routed, the planner takes over. Think of the planner like an executive chef in a highly demanding kitchen. It takes that complex request and breaks it down into a very specific recipe of discrete subtasks. First, fetch the numerical stock price. Second, retrieve the latest news articles. Third, summarize the whole shebang together.
Section 3. Speed and the parallel execution layer.
Now, the absolutely crucial point is how we execute those subtasks without making the user wait forever. Because in production, latency is the ultimate enemy. If our system was still just a basic prototype, it would run sequentially. It might take 2 whole seconds to search a database for documents, and then, only after that finishes, it takes another 2 seconds to call an external API. That is 4 seconds of dead air. In a modern application, a 4-second delay is just incredibly frustrating. But by utilizing parallel execution, we fire off the document retrieval and the API calls simultaneously across shared threads. They run at the exact same time, which dramatically cuts that total latency right in half. We get the exact same data, but twice as fast. Section 4. Accuracy, retrieval, and tools. While parallel execution guarantees blazing speed, we absolutely cannot allow our model to just guess the facts. LLMs are incredible at language, but they are notoriously bad at math. Seriously, do not let an AI do your taxes. So instead of letting it guess today's stock price or try to hallucinate a massive calculation, we equip it with deterministic tools. By giving the system access to a calculator, a database, or a live weather API, we absolutely guarantee a mathematically and factually correct answer. At the exact same time, we're using a process called RAG, Retrieval Augmented Generation. Our retrieval pipeline searches a vector database to fetch the exact latest news articles about Tesla. Then, our prompt builder steps in. It takes the original user question, tightly packages it alongside those deterministic tool outputs and the retrieved news facts, wraps it all in system instructions, and finally prepares it for the model. Section 5. The LLM and caching layer. With a perfectly constructed, fact-checked, and context-rich prompt ready to go, we arrive at the star of the show. But how we deliver the answer is honestly just as important as the answer itself. To create a really dynamic, engaging experience, we stream the response. Instead of making the user stare at a blank loading screen for 15 seconds while the model generates a complete paragraph, we send the text back instantly, token by token, right as it's being generated. It feels fast, responsive, and completely alive. But what happens if 5 minutes later, someone else asks the exact same question? Well, that is where our cache layer steps in. Before we even send the prompt to the expensive LLM, we check our cache. If we've seen this query before, we return the stored response instantly. This is a massive production secret. It drastically reduces GPU load, slashes latency to zero, and saves an absolute fortune in operational costs.
Section 6. Safety and Orchestration.
Let's zoom out and pull back the curtain entirely. Throughout this explainer, we've talked a lot about conceptual layers, but in real enterprise environments, those concepts are powered by battle-tested, heavy-duty technologies. Your API gateway? It's running on Nginx. Your parallel tasks are being queued up by Kafka. Your RAG documents live inside Pinecone. Your instant cache is powered by Redis, and every single millisecond is being relentlessly monitored by Datadog. And because production systems live in the real world, where servers crash and users constantly try to break things, we wrap this entire architecture in strict guardrails. We filter inputs for malicious prompt injections, we track every single token to ensure we aren't burning cache, and crucially, we build in fallback systems. If an external model like GPT-5 or Claude suddenly goes offline, our orchestrator immediately reroutes the request to a smaller, local model to ensure our application stays online without skipping a beat. So you've now seen the full journey of a prompt. You understand the complex symphony of coordinated microservices required to make AI fast, safe, and truly scalable. We've moved far beyond the simple demo and into the intense realm of enterprise orchestration. Knowing all of this, the only question left to ask yourself as you build your next AI application is, your prototype might work, but is it truly ready for the real world? Thanks for joining me on this explainer, and I will catch you on the next one.